what we have been studying is the time evolution of the fraction of neutrons. So this was given by the number of neutrons divided by the number of neutrons plus number of protons, and this one is also called NP. And then we had a differential equation which tells us how it evolves as a function of time. So this involves minus lambda n goes to p xn plus lambda p goes to n 1 minus xn. And it simply reflects the fact that it's given by the fraction of neutrons times the rate at which the neutrons are getting converted to protons, that contributes negatively, and then the fraction of protons and the rate at which the protons are getting converted to neutrons. We also saw that the expression for this is given purely in terms of the temperature, T and T nu. Okay, so these are functions of T and T nu. But if we set mu e and mu nu to 0, okay, and we said that for the time period that will be studying this, okay, we can set mu e and mu nu equal to 0. Okay. These, on the other hand, we have already determined earlier by solving the standard thermodynamic equations of the electron, photon, neutrino system. Okay. So this is an ordinary differential equation in one variable, right? The right hand side is known, so we just have to plug in and solve. So what I'll do first is to give the result of this calculation, okay, what one finds. Okay, so I'll make a table like the way we made a table for the T over T nu result. So here we have temperature. Temperature is the time at which the temperature is reached, and Xn. The convention that I'll be using will be slightly different from the earlier table. Okay. Earlier, if you remember, we started time equal to 0 at 10 to the 11 Kelvin. Okay. So today we'll start at infinity. Okay, when we'll say time t equal to 0 at t capital T equal to infinity. Okay. And this will basically cause a shift of 0.01 in the time scale. Okay, so we shall see why.
So this equation, which is a first order differential equation, will have one initial condition.
Exactly.
So that is set by observation.
No, that will be set by thermodynamics. Okay, because we have seen that for T large, right, Xn was given by this e to the minus q by t over 1 plus e to the minus q by t. So this will be the initial condition, right? This is because at high enough temperature, just thermodynamics determines what the ratio is, right? Equilibrium thermodynamics. So that will be the initial condition. Okay. What will be the input? Okay, will be the baryon density. Okay, that has not entered so far, but later on it will enter. Okay, not for this calculation. Okay, for this calculation you don't need any additional input. Okay, so 10 to the, so this is T and K Kelvin, 10 to the 12. Okay, and let me remind you, 10 to the 12 is about 86 MeV. This is T in seconds, 0.0001, and Xn was 0.4962. Okay. This is statistically this factor over here. Okay. Because T is much larger than Q, okay, e to the minus Q by T is almost 1. Okay. It's 1 over 2, just half. Okay. So roughly half are neutrons, half are protons at such high temperature. Okay, number is slightly less because of this e to the minus Q by T factor. Okay, 10 to the 11. is 0.0099. That's about 0.01. Right? So in the earlier table, this was set equal to 0. Okay, so if you compare this table with the earlier table, you will find a shift of 0.01. Xn is 0.4626. Okay, so you see the number of the neutron fraction is coming down. This is 8.6 actually. Okay, thermodynamics is still good enough. Okay, you can, but e to the minus q by t has also become a little larger. Then 3 times 10 to the 10. That's 0.21106, 0.3798. Now I am of course not making any attempt to put any error bars. Okay, this is just what you get by direct calculation, but there are of course various error bars that you have to worry about. Okay, we can just stop here. Basically, what you will see, okay, this will be seen later, is that this is roughly the place. This is the temperature at which the heavy nuclei start forming, and this process stops. Okay, within 10%, we will argue that this is the temperature at which the heavy nuclear formation takes place. Okay. So basically, this number is the important number. Okay, the fraction of neutrons that was there at this time.
Sir,
Yes.
whenever the heavy nucleus form, the number of proton and number of neutron is same.
No, they are not the same, right? Because Xn is a neutron fraction, right? So rest is proton. See, what you are calculating Xn, right? This is a fraction of neutrons.
So basically, what I am trying to say, when the nucleus forms, so inside the nucleus, so number of proton and number of neutron is same.
No, hydrogen has only proton, right? No neutrons.
Gotcha.
So it's not that all nuclei have the same number of hydrogen, protons and neutrons, right? So helium, yes, helium is true. Helium has the same number of neutrons and protons. Right? But there will be various other things which you'll see don't have the same number.
So the last entry, does it also incorporate the formation of nuclei, or just it's just
No, if you just evolve it, then this is what you'll get, right? But I mean, once the nuclei start forming, right, then of course you have to change these equations, right? Because other processes are becoming important, right? So far, we have been only considering the weak interaction processes where the proton gets converted to neutron and neutron gets converted to proton. But once the nuclei start forming, you have to take into account all the other processes, right? So you shouldn't trust this table below this anyway.
So means the main state as 3 to 10 to the power 8.
Yes.
So it calculates the free neutron.
Exactly. So this is not trustable, right? Because other processes become important, right? So you have to change the equations.
So this temperature for the nuclei formation ratio today?
No, that will be predicted. So you have to actually see what's the temperature, right? So basically you have to see the various processes, right, when they become important, right, and based on that we will determine this temperature. But if we knew the hydrogen to helium ratio, you could predict this, right? We just go backwards, right? But that's not the way it's derived, right? I mean, there is a independent argument as to how to fix this temperature.
Temperatures at which proton and neutron combine to form heavy nuclei, that is like known physics, right?
Yes, it's known physics.
So
Right?
that is something.
Exactly, it's a known nuclear physics, so that's what we'll try to determine.
So this can be used as a test for the correctness of the theory, right?
Exactly, that's right. And as we have been saying that basically it's a question of how fast this is falling off, right? This time is important, right? And if we add some new particles, right, light particles, which would have changed the expansion rate in the early universe, right? It will change these numbers, right? And the results will not agree. So this is used to put bounds on what kind of particles you can add in the theory, for example, right? Or it can be used also to put a bound on the chemical potential of the neutrinos, as we discussed, right? Because if the chemical potential of the neutrons is too big, right, then again the expansion rate will change. Are there other questions? So this part, right? This part we derived earlier. This is not something is being derived here, right? This is what we derived earlier from thermodynamics of the E plus E minus gamma nu system. Right? It is this part which is being calculated by solving those equations. Okay.
Sir,
Now, yes.
one thing, from the data we can say that the fraction of proton is increasing, but the number of free proton, is it increasing or fixed or decreasing?
Well, it's see the total number of course is going down as 1 over a cube, right? Which in this case is going down as t cube, right? As t is increasing, sorry, as t is decreasing, right? The density is decreasing because the universe is expanding, right? So that of course is always there, right? So the density of protons or density of nucleons is decreasing because of that feature, but at the same time the fraction of protons is increasing.
So these are the basically free neutron or free proton here. The neutron or
Xn
proton
is
that
the
not bounding
ratio of the number of neutrons to the total number of nucleons. See, both go as 1 over a cube, right? So that 1 over a cube gets cancelled out. That's why I'm using Xn, right? The fraction of neutrons.
So
See.
are these the free neutron or free proton of the neutron proton?
No. At this stage, we have not taken into account any neutron proton bound state, right? These are only free neutrons and free protons, right? As I said, this is a phase where we will see later that the bound state formation starts, right? And then of course you have to change the equations, right? Because the equation that you are solving, this equation, right? This doesn't take into account any bound state formation. Okay? This is only free neutrons and free protons getting converted to each other by these three processes that we described earlier. Is this clear? Now, just to get some insight into the physics, let's try to check what exactly is responsible for this kind of evolution. And to do that, let's go back to the expression for lambda rate p goes to n that we had written down earlier. So this was given by A integral minus infinity to infinity dq 1 minus ab square over q plus q square to the power half And let's suppose that you are working at T less than MeV. Okay, in fact, small component MeV. Say 1/10 MeV. Maybe I should put some MeV numbers here. So this should be 0.086, sorry, 0.86. That's about an MeV. Okay, 10 to the 10. This is 0.086. Okay, so let's suppose we are working in this region. Okay, and you have to see what in the differential equation. Differential equation was dxn dt was what, minus xn times lambda n goes to p plus 1 minus xn lambda p goes to n, right? These are the differential equation. And you have to just try to see what are the dominant terms in this differential equation. Okay, because later on we need to understand the physics near this temperature reasonably well to fix at to be able to fix the temperature at which the nuclear formation starts. Okay. So if you look at, so T is 1/10 of MeV, right? So that's good enough. T is much less than MeV. This term over here, you see that if Q is larger than minus Q, okay, or say Q by T is larger than minus Q by T, then this term is large, right? Because Q plus Q over T is large. That makes this contribution small. Is that clear? Okay? Large exponent in the denominator. So this means that Q by T must be smaller than minus Q by T. Smaller than or equal to. Right? For this to contribute, for this integral to contribute. But in that case, this contribution becomes 1 plus e to the power Q by T nu. This contribution becomes larger than 1 plus e to the Q by T nu, right? Because I'm just setting Q by T equal to minus capital Q by T. And this becomes large. Because Q is of the order of an MeV, right? 1.2 MeV. T nu is of the order of T, right? So this ratio now becomes large. So in either case, okay, for the whole range of integration over Q, okay, you see that either this is large or this is large. Is this clear? Okay. So this integrand always has a large denominator, okay, which basically means that this is small.
So why is that origin large?
Why is what large?
The last part you have said, the 1 plus e to the power T by T.
Because Q is of the order of an MeV,
Yeah.
right? And T nu is of order T. Right? T nu by T, of course, we have calculated, right? Some 1 over 1.4. Right? So if Q is MeV and this is T nu, right, which is we are taking about say 0.1 MeV, right? That's of the order of 10, right?
Yeah.
And e to the 10 is a large number,
Large.
right?
So it will be the contribution to the small.
Yeah. So either, so that means that for the range of Q, right, between minus infinity and infinity, either this is large or this is large. Right? There is no value of Q for which both can be kept small or of order 1. Right? So you always have a large denominator. Right? And once you have a large denominator, its contribution becomes small. Is this clear? So that's what he said. So this contribution is small. So the lambda p goes to n is a small contribution. Okay? So in this equation, this one doesn't contribute very much. Okay? Now physically it's clear why this should be the case, right? Because after all, what are the processes that converts to P to N? Right? Is a collision of positrons and neutrinos. These are the kinds of collision of electrons or neutrinos, right? These are the ones which converts P to N. Right? But as the temperature is becoming less, right, the typical energy of electron or a neutrino is of order T. Right? And that's much smaller than an MeV that is needed to make a proton into a neutron. Right? Because the neutron proton mass difference is of the order of an MeV. Right? So to have this process, right, to convert P to N, you have to pick photons or neutrinos, okay, not photons, neutrinos or electrons, which have energy of the order of an MeV. And those numbers are very small, just thermodynamics, right? The Boltzmann separation. And that's the reason why this rate is small. P to N ratio rate you can ignore.
And in this temperature, the electrons are, we can consider also to be non-relativistic.
At this temperature, yeah, electrons are more or less non-relativistic. But the Boltzmann separation, of course, is there both for relativistic and non-relativistic particles, right? To get an energy of order E, right, you have an e to the minus E over T separation, right? And that's what you are seeing here. This Q over T that you are seeing is really E over T, right? That's the kind of energy that the electron or a neutrino has to have in order to be able to convert the proton to a neutron.
So Q is energy of proton minus energy of neutron.
Energy of neutron minus mass of neutron minus mass of proton. Exactly. So Q was Mn minus M. And this was of the order of 1.293 MeV.
In either case that we are getting a suppression.
In either case, you are getting a suppression, right? So which means that throughout the range, the whole range of Q, right, this integrand is always suppressed. There is always a large exponent in the denominator. Is this clear? Okay. So I'll now do the similar calculation for n goes to p. Okay. And the difference between p goes to n and n goes to p, as we had discussed, is that I just have to change the signs here. Okay, that's what we had written down earlier. So let's do that. N goes to p will be here plus and here minus. Is this clear? I should have, well, I didn't say it, but it's clear that this integration, of course, excludes. We have to have q plus q larger than AB. Otherwise, this square root doesn't make sense. Okay, so these are always there, both for neutrons and protons. Okay, but that's not going to be very important. So now let's look at this and see in which range we can get a reasonable contribution, right? In which range the denominator is not large. So first, q over t nu must be less than 0 or of order or of finite number around 0, right? It cannot be very large or negative. Okay? That's what this symbol means. Q over t should be less than 0, or if it's not less than 0, it's of order 1. This one tells us that q plus q over t must be greater than 0 or of order 0.
Sorry sir, small q, what is the order of the small q?
Q is been indicated.
Oh, okay.
Q is the integration variable, right? So we are trying to see in which range of this integration variable small q we can get some appreciable contribution, right? In which range is the denominator not so big? Right? That's what we are trying to determine. Right? And what you are saying is that in order that the denominator is not so big, okay, this term has to be negative, this exponent has to be negative, and this exponent has to be negative. Right? Which means this q plus q over t has to be positive. Okay? Now when I say it has to be positive, it doesn't have to be strictly positive. If it's negative, it cannot be very large and negative, right? It has to be around 0. So this can be translated by saying that q over t is greater than or equal to minus q over t. roughly the contributing range is minus q less than q. Okay, so this is the range from which you can get some appreciable contribution.
But sir, for proton to neutron, no such type of range.
No, for proton to neutron there is no such range, right? So the contribution is completely small. For neutron to proton, right, there is a range which can give appreciable contribution, right, and that's what contributes. Right? So this is not small. This is not necessarily small, right, but it gets contribution from this range. Is this clear? Okay. Now the reason that we are going through this is, if you recall, that here I have written a single integral, but this expression actually is a sum of three different processes, right? Three different processes, each giving its own range of integration. And if you go back to your notes and see which range, which process contribute to this range. You remember which process contribute to this range? That's a neutron decay. Okay. So what it is saying is that when the temperature is small compared to an MeV, right, then the dominant process that contributes to this neutron to proton conversion rate is as a neutron decay, okay, which is again quite physical, right? Once the temperature has come down, right, the neutron is traveling almost in the vacuum, right? There is no background. The background electrons and background neutrinos have all become quite small, right? So they are the only process that will dominate. If the neutron was strictly in vacuum, right, then the only process that can convert a neutron to a proton is a neutron decay. Right? There is no option of neutron colliding with anything to become proton, right? Because there is nothing else in the vacuum. And that's what you are seeing here. Right? The major contribution to this process comes really from neutron decay. Is this clear? Okay. So here, I mean, why is this important? This is important because suppose we know that here, okay, this happens within some given time span. Right? We cannot fix the time exactly, but there is some error. Okay? And you want to know that error in time, how does it translate to an error in this? One way is to just do the full evolution, right? We just see how final evolution and see how it changes, right? If there is an error of say 10% in determining the time, right, how does it affect this number? But a quicker way is to say that because the neutron decay is a dominant process, right? Suppose there is an error of 10 seconds in the time determination, right? Then you simply see in 10 seconds how much will xn change, right? And how will xn change? Because the neutrons decay. Right? Neutron lifetime we know is about 880 seconds, right? Half-life. So using that we can determine how much fraction of the neutrons would have decayed in 10 seconds. Right? And that's the way you can convert this to an error in this fraction. Okay? Because eventually, of course, we will not be able to determine the time exactly. We will determine it only up to an error, right? At which this nuclear formation started, right? And that error will translate to an error in the fraction of neutrons that was there at that time. Is this clear? let me now describe the major processes that are responsible for the nucleon formation. For nuclear formation.
So how much is this error usually in Excel due to this 10 seconds error?
It will be about, I think, 10% error. Yeah. Right. Yeah, we'll make this error estimate in more detail later. Right? It will be after that, of that order. Okay. So the first step. See, here we have a gas of protons and neutrons, right? So they have to start binding. So the first step in this binding is the binding of proton and neutron. So this is an electromagnetic process because there is a gamma involved. Then there are a series of things that happen. Okay, these are the major processes. These, as you can see, are all strong interactions. Okay, because it doesn't involve any neutrinos or any photons.
The second equation that will be helium 3 deuterium plus deuterium.
Yes. Something is wrong here.
No. So
This one.
no above.
This one.
Yeah. H E in the right hand side.
No, this is hydrogen.
Hydrogen.
Yeah. This is the unstable hydrogen, right? Because you are getting out a proton, right? So it has only one proton and two neutrons. So this, of course, even if it forms at that time, right? This is not going to remain in the today, right? Because I think it has a lifetime of some 12 years or something. Okay? So it will just decay by today, for the cosmological time scale. But these are the intermediate stages that we need to go through, okay, for this formation. The important point is that we cannot form these before the neutron forms, right? Because to form this directly, you need to have multiple particles coming together, right? And that did happen for electrons and neutrinos because their densities are high, thermal densities, right? But the density of the nucleons, that baryon density, as you have been seeing, right? Nb over n gamma is 10 to the minus 9. So the probability that two of the protons come together, right, is already down by a factor of 10 to the 9. So the probability that more number of particles will come together is very low. Okay, that's why the formation happens via these two body processes.
So first the electromagnetic process has to be done.
First, the electromagnetic process has to be done.
Then the rest will come.
Then the rest will follow. No, just because P plus N, right? When you P plus P, right? What can it do? It doesn't bind, right? There is a bound state of two protons, right? N plus N also doesn't bind, right? So P plus N is the first bound system, but P plus N cannot just go to T, just by energy conservation, right? It has to emit something, right? It can also emit neutrinos and electrons, but those are weak interaction process, right? So the electromagnetic interaction is much faster. So this is the first process that can happen. So if you want an accurate analysis, then what one has to do is to introduce. Okay, let me give that step anyway. Right, what you should really do if you want a complete analysis. So if you want a complete analysis, right, what one has to do is to basically set up the, suppose yi is equal to the number of nuclei of type I. Okay, which can also include protons and neutrons, divided by by NB. Okay, it's always useful to work in terms of ratios. Then we can set up equations dyi dt, equation for dyi dt, dy n dt, and dy by y p dt. And the right hand sides can be obtained by knowing the strength of these processes. Right? All of these, of course, are standard nuclear physics processes. Right? So you can measure their rate, right? And you can put them on the right hand side, and solve the equations in the same way that you do it for the xn's. Right? There it was only one variable. Here it will be multiple variables. Right? Because different things get converted to each other. Right? For example, the Neutron ratio can change because of this and because of all of these. The helium 3 can change because of several things, right? This will affect it, this will affect it. So these, you can set up these equations in that way and solve them numerically. I will run over D, H3, He3 and He4. Right? These are the 4 different kinds of nuclei, right? And you have also P and N. So P and N I have written separately. Okay. Right? So at any given time, right, the gas is a mixture of protons, neutrons, and all different kinds of nuclei. Right? I am not including the heavier ones, right, because their numbers are really very small, so you don't have to worry about the heavier nuclei. But all these will play a role.
So this will be our evolution equation after the during the nuclei formation.
Exactly. Right? And then you can just solve them. Find out how the number of nuclei evolve, right? And what is the asymptotic values of this number of nuclei. Okay. So that will be the, correct way to do this if you want the exact numbers. But what we will do is to take a shortcut and we will make some approximations and get the numbers which are quite close to the exact ones, the correct ones.
What is this NB?
Oh, NB I am defining as the number of baryons. Total number of protons and neutrons, free protons and neutrons, as well as everything that is there in the nuclei. Right? So NB by definition is the total number of baryons, total baryon charge. Okay, that's just a matter of choice, right? I could have divided it by the number of protons. Right? I just want some ratio, that's why I used something in the denominator. So let me now describe the approximate analysis. This will require some assumption, but we will justify it eventually. So what is the bottleneck here? You see, right, as you have already noticed, that the first thing that has to form And we will see that at sufficiently low temperature, okay, low means not lower than what we have studied, but at the kind of temperatures that we will be interested in, like 10 to the 9 K, this process is already in thermal equilibrium. So you can actually accurately predict the number of deuteron based on just thermal ensemble, okay, the Boltzmann's formula. Okay, and we will write down the correct expression later. Okay, it's the same formula that we have been writing, right? The number density of deuteron, right? You have to basically use the formula that we have been writing. But that number density we'll find is small. Because the number density is small, these processes, even though this is strong interaction, but all of these depend on the deuteron number density, right? So because the deuteron number density is small, these processes remain out of equilibrium. Okay, the formation doesn't really happen very much, right? Because the number of deuterons is very small. So at some point, once the number of deuterons reaches a critical density, okay, which requires temperature to come down, because as the temperature comes down, the number of deuterons we'll see is going to go up. Once the number of deuterons reach critical density, okay, and these processes become important, then the strong interaction takes over, right? Then the thermalization rate is very fast. Okay, here. And basically, within a very short time, okay, and that's the error that we'll have to estimate. Within a very short time, the system thermalizes. So then we can again apply the thermal formula, the formula for thermal equilibrium, thermal and chemical equilibrium, for all these systems. And once we can apply the formula for thermal equilibrium, we can calculate the fraction of particles of each type. Okay, so that's the principle we'll be using. Namely, that we'll assume that as the universe is cooling down, at some time Ti, okay, when the number of the deuteron density has built up sufficiently, you can apply thermal formula for thermal ensemble. Above that critical temperature, we cannot use the formula for thermal ensemble, okay, because the processes are slow, so that you cannot have, it doesn't thermalize. So we'll first calculate the result based on the assumption that at some time Ti, the system thermalizes.
So you are seeing some critical temperature.
Critical temperature, which also means critical time. Right?
Yeah. So this critical, you are saying that to reach for the deuteron to the critical density so that the other processes can work.
Exactly.
Yeah.
So the other processes become important enough and the system thermalizes. See, till these processes become important enough, the system is not going to thermalize, right? It's going to preserve its original densities. Right? So once the system reaches this critical temperature, then you can apply the thermal distribution formula and calculate the numbers of these objects. Okay? So that's the philosophy. That's the procedure we'll be following. Okay? So the difficult part here, or relatively difficult part, is to determine at which temperature it happens. Once we assume that it happens at some temperature T, then applying the thermal distribution formula is straightforward, right? That we have been doing all along. But so we'll postpone the determination of the critical temperature till later. But assuming that there is some critical temperature, okay, which happens to be this 10 to the 9K that we have been mentioning. Okay? That 10 to the 9K is when the neutron density is about 1.13, the neutron fraction. Okay? Assuming, okay, that the system thermalizes at that critical temperature, we'll first calculate the fractions of various particles, and later on justify why that is the correct critical temperature. Is that clear?
Actually, I could not understand.
Yes.
Generally, we see whether it is in thermal equilibrium or out of equilibrium by gamma by h.
Yes.
And so here, initially the deuteriums are small, means
Yes.
and it's producing, and then how it reaches to thermal?
Because see, the is gamma is rate per deuteron by the expansion rate, right?
Yes, yes.
But the rate per deuteron, because it's D plus D,
Yes.
right? So the rate per deuteron depends on the deuteron number density.
Right. So
Right.
that is small, so.
That is small. So that's why the system was out of equilibrium. Right? Once that becomes big enough, then the rate of this interaction becomes comparable to the Hubble expansion rate.
Then it thermal.
Then it thermalizes. Is this point clear? So let me state again. We assume that the system thermalizes at time T1 and the temperature, corresponding temperature is T of T1, okay, which is laid out from the table that I wrote down. So the first will calculate yi, yp, yn at T1. Okay, this will tell us how things form. Then we'll determine T1 and hence T of T1 later. Okay, but let me give you the answer anyway. The answer will be that T of T1 is 10 to the 9 within an error of 10%.
So the deuterium formation starts even before.
Even before, yes. But the number density of deuterium
Becomes
remains small, because the one is, the deuterium formation starts even before, right? In fact, this process comes within thermal equilibrium even before, right? But even if you apply the equilibrium formula, thermal equilibrium formula, right? The actual number of deuterons that you calculate from the equilibrium formula remains small till the temperature comes down sufficiently. Yeah, and that has to do with the fact that we'll see later. That has to do with the fact that the binding energy of the deuteron is small. Okay, the systems which have larger binding energy forms easier.
So this is due to the fact that there's no decay process from deuterium. It's only forming.
Well, it may collide with itself, right? Yeah, if there's a decay process, you have to take that into account, right? That's already part of the thermal distribution, right? It takes into account the decay process also, right? That's like for the neutrons, right? When you calculate the extent, right, at high temperature when apply thermal equilibrium, right? It's not that we didn't take into account the fact that neutrons decay, right? Because it has a balance between the decay process and the production process, right? And that's what gave Xn. And as you saw, that in thermal equilibrium, that agrees with what to calculate from thermal equilibrium.
It's like the decay process of deuterium also takes over when the density is sufficiently large, since two of the deuteriums are combined.
Exactly. Right? So deuterium, of course, is a stable particle, right? But its number can get depleted by collision. Okay. So now let's start doing thermal equilibrium. So NP is the number of free protons number density of free protons. Nn will be the number density of free neutrons. And Ni will be the number density of nuclei of type I. Okay. And again, I will run over DH3, He3, He4. So there are two conserved charges. Once the system starts, see, weak interactions have gone out of equilibrium. Okay? So you are not worrying about talking about weak interaction at this stage. Okay? At the time T1, right, weak interactions are of course responsible for why Xn was changing earlier, right? But at time T1, okay, we are saying that that process stops. Strong interaction, electromagnetic interaction, basically forms the nuclei. Right? And after the nuclei have formed, there is no decay. Right? Unless you form some H3, right, which will decay into He3. Okay? Otherwise, there is no decay. So the weak interactions are not relevant at this stage. Once the weak interactions are not relevant, then the total number of neutrons and total number of protons are individually conserved. Okay? There is nothing which converts protons to neutrons and vice versa. Is that clear? Okay. But once the neutrons form part of the nuclei, right, then there is no decay. Okay? And in any case, that process is much slower than the strong interaction process. Right? Here you are talking about a very small window near T1, right? What's happening in that window, and in that window you can forget about the number of neutrons changing.
Yeah, Neutron decay is also electroweak process.
Pardon?
Neutron decay is also electroweak process. It mediated by double.
Weak interaction process.
Yes, sir.
Yes. So it's a very slow process, right? And the kind of time scale that you're talking about, right, is much smaller than the decay time of the neutron. Right? Neutron half-life is about 800 seconds or close to 900 seconds. Right? So the kind of time scale that we'll be talking about is much smaller than that, right? Because this thermalization happens more or less instantly. Okay, in that over that time scale. So we'll ignore the weak interaction process, okay, and treat the number of neutrons and number of protons as individually conserved. There will be two conserved charges. Okay. And because there are two conserved charges, we have to introduce two chemical potential, right, as we have been doing. So in Q, we have to insert exponential of mu tilde 1 times Nn total number of neutrons, plus mu 2 tilde times Np total. And what are these? So Nn total will be Nn number of free neutrons plus whatever comes from the inside the nuclei. That will be sum over I, Ei minus Zi times Ni. Ai is atomic number. Ai is the number of neutrons plus protons in per nuclei. Per nuclei. And Zi is the number of protons per nuclei. Pardon? Multiplied by? Yeah, beta. Similarly, this one is given by Np plus sum over I, Zi Ni. Right? Because there are Ni is the number density of the IF nucleus, but the IF nucleus, each of the IF nucleus contains Zi protons. So that's why it's this. So we write this as mu1 tilde nn total plus mu2 tilde np total. We will write as mu1 un nn plus mu2 sum over I. And by comparing this with this, we lead out the expressions for mu n, mu p, and mu I in terms of the mu1 tilde and mu2 tilde. Right? This is what we have been doing earlier also. Right? When they have multiple charges, but only some of them are conserved. Right? We introduce only two independent chemical potentials, or a number of chemical potentials equal to the number of conserved charges. But then we express each the chemical potential of each species in terms of those independent chemical potentials. And that's the way we proceed. So this comparison tells us that mu p is mu2 tilde, right? Because np total has np total has np. That's the only place where np appears. So mu n is mu1 tilde. And mu I is ei minus zi times mu1 tilde plus zi mu2 tilde, which I can write as zi mu p plus ei minus zi times mu n. So there are two chemical potentials which you can take to be mu p and mu n, or mu1 tilde and mu2 tilde. And what determines them? What determines them is the individual neutron densities and proton densities at time t1. Right? Because we are saying that this at t1 the system formalizes. So at t1, right, you look at the individual number of neutrons and number of protons, and those will be the input parameters for calculating mu p and mu n.
Sir,
Yes.
is it NNQ or Q?
Pardon?
NNQ or
This is in Q, sorry, not in Q has this. Okay, inside the sum. But Q of course is not just this, right? It has sum over states with also minus beta again. Is this okay so far? So now we can write down the formula for NP, NN, etc. And we will be, all of these particles are non-relativistic, right? So we'll be using the non-relativistic formula that we derived. Okay, instead of writing down the full relativistic formula as an integral. So NP, let me write this down. I think this is should be familiar. 2 e to the power minus MP minus mu p formula for Mi will be Zi MP plus Ei minus Zi Mn minus Bi. Okay, what is Bi? This is the binding energy.
Sir, how can you write this for Ni, because this is true for NP and Nn, but here Ni is the nuclei.
Yes.
So is this distribution also true for this nuclei?
Yeah, as long as they are in thermal and chemical equilibrium, which you have been assuming, right? That is another kind of particles, right? After all, we apply statistical mechanics to oxygen molecules, right? Even though those are not really fundamental particles.
So we can treat them, these particles, as some fundamental particles.
Exactly, some new particles, right? Which can all get converted to each other, right? And that we are allowing here, right? Because we are taking only two independent chemical potentials instead of individual chemical potentials being independent.
Sorry, Ni, will there be a two factor because this two
Oh, sorry, for 2, it will be Gi. It will be Gi. This is the number of degenerate states. Okay, so typically because of the spin of the nuclei, right, it takes some value. These are of course only nuclei, right? The atoms haven't formed yet. So when you are talking about the number of states, it's really just the number of nuclear states that you are counting. So Yi is Ni over Np. So you can calculate, and Y similarly Yn and Yp. Yp is Np over Np. Yn is An. Let me write this here and I'll erase this. So what are you supposed to do? You are supposed to eliminate mu p and mu n from these equations. Right? Mu p and mu n have to be determined. Right? Mu p and mu n are determined in turn in terms of the xn's. Right? We'll write down the precise equation later, but in principle, those are the two data, xn and 1 minus xn, which are the number densities of the neutrons and the protons. The total number of neutrons and protons. Those are the numbers you have to use to determine mu p and mu n. But we can try to make our life simple by eliminating mu p and mu n from these equations. Okay? And the reason that we can do this is because the dependence on mu p and mu n is very simple, right? This is mu I here, mu n and mu p. Okay? So this means that if we take, for example, np raised to the power zi, right? And nn raised to the power ai minus zi, right? The exponent that we get is the same as the exponent mu I that is sitting here, okay? Because of this relation over here. Okay? So you can take combinations of nn, ni, np and nn for which the mu's just drop out. Is that clear? So we'll write down the relation in terms of the yi's. So this I'll leave as an exercise. Okay, and explain what goes into this. So yi over yp to the power zi, ya, yn to the power ai minus zi. This is nb to the power ai minus 1 times Ni over np to the power zi nn to the power gi minus zi. Okay, this is a trivial statement. I just counted the powers of nb that we get from these various things. Is it okay? Right, because np will give you, each np will have yp times ai. Sorry, each np will have times nb, right? So you'll get a power of nb to the power zi from here, nb to the power ai minus zi from here, okay? And one power of nb from here, right? And that's what is being compensated by this nb to the zi minus 1. But this combination we can now calculate from here, okay? And you can see that they have adjusted these exponents in such a way that the mu i's drop out. Furthermore, in the exponent, right, the combination that appears is exactly mi minus zi mp minus ai minus zi mn. Okay, so what is left is the binding energy. Epsilon, the definition is half nb emp over 2 pi to the power minus 3 by 2. Okay, there are some approximations I have made, so let me explain. Is this expression clear? Okay, I got this just by substituting the ni, np and nn from here. Okay, the exponents we can easily check, gives you e to the bi by t, and then the rest of the factors, these factors that we see here, these are the ones which give you this epsilon to the I minus 1. Okay, but let me explain what approximation I have made. The first approximation that I made is that here, in the product, right, not in the exponent, I have set mn and mp to be equal. Because the difference between mn and mp is small, right? So we don't make that much error. In the exponent, we will make a lot of error, right? But not in the multiplicative factor. Similarly, mi, I have set equal to ai times mp. Okay, because it's actually what? Zi mp plus ai minus zi mn minus bi, right? But the bi is small. The binding energy is small compared to a GeV, right? So bi I have ignored, and I have set mn and mp to be equal, so that it just becomes ai times m. Okay, and that's in fact the origin of some of these ai factors. Ai to the 3 half that you see here is basically coming from there. This mi over here. Is this clear? So this gives you y in terms of yp and yn. This side is all known. Okay, once you fix t, okay, everything here is known. Okay, I'll try to elaborate on this a little more, but you can convince yourself that on this side everything is known, right? NB, we know NB at this point, right? We know NB today, right? And we know the temperature at which you are working, right? So NB will just get scaled by this A over A cube factor, right? Which means by the T cube factor, right? T over T naught cube. So everything that once T is given, everything we know here. Okay? So you have two unknowns, yp and yn. Right? So you have to find two more equations to determine those. Okay? And those are the equations for the total charge, total number of neutrons and total number of protons. Okay? So what are those? Those equations are simply yn plus sum over I ai minus zi times yi is xn. This is the fraction of neutrons that we have at time t1, and yp plus sum over I zi yi is 1 minus xn. So this is a complicated nonlinear set of equations. We will see that it's not very difficult to solve them. But there is no differential equation involved. Now it's purely algebraic. Right? Because each of these yi's are given in terms of yp and yn from this. Right? The right hand side is just a constant that you can calculate given t. So you just substitute and you solve for yn and yp. Okay? Because these are known from the table. Right? Once you have fixed your temperature. Is this clear? So NB, so NB is A0 over A cube times omega B rho C over NP. Okay, so what is it? What have we done? Rho C is the critical density today. Rho C, we had given the expression for rho C in terms of Hubble constant, right? It is 380 square by 8 pi. Okay. So omega B rho C is the baryon density, right? The density of the energy density due to baryons. Okay. We are interested in number density, right? To get the number density, you have to divide by the mass of each particle, right? That's MP. Okay, we are not distinguishing between M and N. So mass of each particle. So that's what was the number density of what is the number density of baryons today. Okay. But you have to multiply it by A0 over A cube, okay, to calculate the number density of baryons at early time. Right? A0 is the A0 today, and A is the A at the time that we are considering, A of T1. This I can also write as T of T1 over T0, okay, which is 2.73K, 73K cube times omega B rho C over M. Okay. So omega B we know is about 0.04, is 0.04. And the Hubble constant H0 is 170 roughly 70 kilometer per second plus megaparsec, and 1 megaparsec we had said is 3.086 times 10 to the 24 centimeter. So this basically says that if two objects are separated by this distance in the universe, their average relative velocity is 70 kilometer per second. Okay? That's a measure of the expansion rate. So you can basically substitute this expression for NB here and calculate epsilon. Okay, everything else is fundamental constant. MP is the mass of the proton. And I'll leave as an exercise to check that epsilon is a number of order 10 to the minus 15. Okay, that gives you the order of magnitude of epsilon. Now you would notice from this formula that the more the number of AIs, the smaller is this factor. Right? That means it's less likely, at least from this factor, it looks like that it's less likely to get nuclei with large number of nucleons, large number of baryons, right? And the reason is simple. Okay, the physical process that forms those requires either multiple nuclei coming together, right, which is small because the density is small, because the baryon density NB which has gone in is small, or it requires multiple processes, right? That first a proton and neutron has to collide to form deuteron, then deuteron has to collide with something else to form helium and so on. Right? So nuclei with larger number of nucleons require more effort to form, right? And that's what is being seen by this factor, epsilon to the I minus 1. Is this?
Epsilon is a small number.
Epsilon is a small number, and the reason that it's small is, to a large extent, is because of the smallness of NB. Right? The NB over N gamma, right? You have seen like 10 to the minus 9. Right? That's a large part of the reason why epsilon is small.
So you are saying that is why that heavy nuclei
Are less likely from this formula, right? The heavy nuclei are less likely. Okay, that's the physics. That because the density is so low, right, for things to come together and form a heavy nuclei, the probability is small.
Just one minute.
Yes, sir.
T0 is the temperature basically when the baryon freezes out.
When the baryon freezes out. So I am considering the T, so this is for T of order 10 to the 9k. Okay, otherwise there will be a factor, it goes as T to the power, so otherwise I should write epsilon as 10 to the minus 15 times T over 10 to the 9 Kelvin to the power 3 half. That's the correct formula. Because T to the 3 half, you can see there's a T cube coming from here, right? And there's a T to the minus 3 half coming from here. Okay, so it's normalized so that at T equal to 10 to the 9k, it's 10 to the minus 15. Right? At any other temperature, there is a factor of T over 10 to the 9k to the power 3 half. So now let me give these factors. These factors. Put this there. E to the bi by t. Again, we give it for t equal to 10 to the 9k. But this one you will see has a very strong dependence on t, right? Because it's an exponent. Okay, but let's see what for 10 to the 9k what it is. For helium, 4. helium 3 is 10 to the 39. H3 is 10 to the 42. And for deuterium is 10 to the 11. This number 10 to the 142 for the helium 4 is a reflection of the fact that the helium 4 has a huge binding energy. Okay, like 28 MeV. So that's why at this temperature, right, which is about 0.1 MeV, it's a huge number. It's e to the 280. Right? If it's 28 MeV, right, 28 over 0.1 is a factor of 280, right? That's responsible for this big number over here. And the fact that these are smaller is simply a reflection of the fact that their binding energies are not as big as the helium 4. Right? So helium 4 is the most stable nuclei in that range. Is this clear? So I'm not going to apply it here. So you get YHE4, okay, order of magnitude. Okay, these numbers will not be very relevant. GI and AI to the 3.5, right? These are all of order 1. Okay? The relevant ones are this one and this one. So this number is like yn squared, yp squared times 10 to the power 97. Where did 97 come from? 97 is 142 minus 45. 45 because you see we have an epsilon to the power ai minus 1, right? So ai is 4 for helium 4, right? So an epsilon cube. Right? An epsilon cube is 10 to the minus 45. Right? That's where this minus 45 comes. Okay. YHE3 can be calculated similarly. It's yn yp squared times 10 to the 9. YH3 is yn square yp 10 to the power 12, and yd is yn yp 10 to the power minus 4. Is this clear? So all the y's are less than 1. They are all fractions, right? Y is the number of nuclei or number of neutrons and protons divided by the total number of baryons, right? So obviously it's all less than 1. So if you look at this equation over here, right, we see that because this number is less than 1, either yn or yp has to be very, very small. Right? Otherwise you cannot balance this equation. Right? So either yn, so let me call this the equation number 1. 1, 2, 3, 4.
Why the balance?
Pardon?
I
This equation you are trying to satisfy.
yes.
Right? This is a number less than 1.
Oh, okay.
Right? This is 10 to the 97, right? So it better be that one of these at least is small.
Both can be also small.
Both can also be small. Okay? So either, so 1 implies that either yn or yp or both small, and that the smaller one is less than or order 10 to the minus 24. because 10 to the minus 24 raised to 4th power is still smaller than 10 to the 97. Okay? So unless at least one of them is smaller than 10 to the minus 24, there is no way you can satisfy this equation. Is that clear? This immediately tells us that all these three are small. Right? Because 10 to the minus 24, any one of them is having 10 to the minus 24 is going to overcome these. Okay? So this implies that Y83, YH3 and YD are all small. So now you just substitute here and solve. So Yn plus 2 YHE4, I am ignoring all the other Y contribution, is equal to Xn of T1, and Yp plus 2 YHE4 is 1 minus Xn of T1. Right? Zeta is 2 for helium 4, Ai minus zeta is 2 for helium 4. So now we also know that Xn is less than half. Right? Because the number of neutrons is always less than the number of protons. The fraction of neutrons is less than half. Okay, we saw that at 10 to the 19k, 9k, it's like 0.13. So Xn is less than half. So this implies that Yp must be larger than Yn. Just compare the two. So hence, Yn must be less than or equal to 10 to the minus 24. So you can ignore the Yn. So now you are done. If you can ignore Yn, this tells us, the top equation tells us that 2YHE4 is Xn. So YHE4 is Xn by 2. And then the second equation then tells us that Yp is 1 minus Xn minus 2YH is Xn. That's 1 minus 2Xn. Okay. So YHE by Yp is Xn over 2 times 1 minus 2Xn. So this is the ratio of the number of helium nuclei to the number of protons. Okay. And nothing else is there. Everything else is very small, right? Because of this fact. What is normally quoted is the mass ratio. MHE, the total mass, M total in HE over M total in proton. A difference is that you have to multiply it by a factor of 4 because the helium mass is 4 times the proton mass. Right? It has 4 nuclei instead of 1. Right? So that's 4 Xn over 2 times 1 minus 2 Xn. So this cancels. So this is basically 0.27 over 0.23. Right? Because Xn at 10 to the 9k, at 10 to the 9k, Xn is 0.133. Two times Xn, sorry, 0.73. 1 minus 2 Xn, right?
Yes, sir.
So 1 minus this, so 0.73. So 27% of helium, 73% of hydrogen. Right? That's what this is saying. Right? And in the early universe, almost nothing was formed. Nothing else was formed. Of course, this is only approximate, right? As I said, if you want to actually find the number of trace elements, you have to evolve by those differential equations, right? And you do find some numbers, some small numbers, but nevertheless they are non-zero numbers, right? So you can predict precisely how much deuterium and other elements are produced in the early universe by following this equation. So next time we will basically try to determine this number. Right? We have been assuming that it's 10 to the 9k where things happen. Right? But what determines this number 10 to the 9k? Right? So this is what we'll try to determine next time. Right? And once we determine this, then the rest is follows from that. Is this clear? Yes.
Just in equation 1, if you just put y, like yn equal to 10 to the minus 24, then yh is also bigger.
YH is also, yeah, so you have to put yn to be less than 10 to the minus 24. Right? Now we know, for example, that yp, right, is of order 1, right? Okay. So if yp is of order 1, then yn has to be like 10 to the minus 50.
Okay.
Right? Or minus 49.
Okay.
Right? To have this satisfied. I just give a bound here.
Okay.
Because at this stage, you didn't know if both can be small. Now, physically, it's clear what's happening. Right? Physically, what's happening is that once the nuclei starts forming, right, there is of course a lot of reaction. Right? It goes to deuterium, helium-3, hydrogen-3, eventually helium-4. But because of the large binding energy of the helium-4, right, it basically depletes everything else. Yeah? Any other intermediate materials that might have been formed in the process of formation, that disappears completely, okay, or almost completely, okay, and producing mainly helium-4. Of course, everything cannot get converted to helium-4 because of the conservation laws, right? Because the number of neutrons and number of protons have been fixed for us. Right? So all that it says is that all the neutrons that were available at that time are used to form helium-4, right? And then you are left with only protons, right, which are there as hydrogen. Right? So that's the underlying physics. And the reason that only helium-4 forms is because of this large binding energy. Right? This number, right, this 10 to the 142 is what is responsible for why this is so much more dominant compared to the others. And as we have been emphasizing that if the expansion rate of the universe was somewhat different, then these numbers will change. This number will change simply because the neutron decay rate, of course, is universal, right? That's fixed by the fundamental laws. Right? So if the expansion becomes faster, right, then the neutrons wouldn't have decayed by the time so much by the time the temperature becomes 10 to the 9k. That there are more neutrons left over, and they'll produce more helium. Right? If the universe had decayed slower, right, then by the time you reach the temperature of 10 to the 9k, more neutrons would have decayed, right? Because more time would have elapsed, and that will affect the prediction of this ratio. Okay, so we'll continue next time.